it was one of the VR productivity apps that I had been messing with, called, was it Immerse? Yeah, called Immersed, that allowed me to have this one screen, but I could have up to 5 virtual screens, even though I don't physically have those monitors. And I didn't like it that way, so I actually went back down to one screen anyways, and just because I like flipping between my screens like this. But I bet you whatever magic that had to do to make that work on there made it so that mirroring became a weird thing. Okay. All right, so last time we talked about all the bit shift stuff, right? And the bitwise ands and the bitwise ors, and we're all good with those types of things. Don't necessarily have a strong idea of why we might use it. I think last time we looked at the idea of masking a little bit, where we can kind of like store multiple values inside of a single register and then kind of be clever about through bit shifting and masking to kind of extract individual values out of it if we needed to. So we can kind of see how that might help. So we're going to look at this from a binary tree implementation of a heap today. So I'm giving us a sample tree, and remember, this is just that first piece. The first piece is, if I have this tree currently and this gold guy, that's the next place that we would land, is kind of that idea, right? We want to discover that location. All right, and I think about it almost like GPS, right? You start at the top, and then you use some sort of mechanism that says, well, do I turn left or do I turn right? And then you're next to the next level. Do I turn left or do I turn right? And we're going to use these bitwise operators to make those decisions. All right. So first thing we do is you figure out how many total nodes are in our tree. All right. So our goal, fill the entire tree, right? That's kind of the thing that's shifted in our mindset when we went on to this heap data structure, is this idea that we're no longer placing nodes where they might belong in a based on the order in which we added them, which gives us that situation of an unbalanced tree that we talked about with our binary search trees, where if we just happen to get unlucky in the order in which we put stuff, it ends up being super lopsided. And then we talked about the idea of a self-balancing tree. I think we looked at what ABL trees, where kind of represented as like it's a chiropractic adjustment. It's out of balance. You kind of do some twists and turns and things like that. So we didn't actually implement that, but we kind of know that something like that exists because there must be a benefit to having trees that are balanced more often than are not balanced. All right. So now when we're dealing with a heap, our goal already is to have a full tree. Now, a full tree, we would say, is by definition a balanced tree, right? We potentially have lost some of that organization within the tree. We do have this heap rule, min-max heap, depending on which one we're doing, but we've lost some of that organization what they have with the binary search tree, but we've gained the idea that the tree is always balanced. Okay, so if we see a tree like this, we could say the total number of nodes in this tree is 10, as I currently have it, right? So we somehow go and figure that out. You can write an algorithm that goes through and just says, okay, well, I'm one plus the depth of my left tree plus the depth of my right tree. I think we wrote that at some point. So we could figure out how many total nodes are currently in the tree and count all the nodes. All right. So if we assume we have a tree with 10 total nodes, how many levels deep is that tree? Well, the 10 is at level 0. The 2 and 4, well, let's just kind of go down here. We want to know what is the depth of this tree, because we might want to know where is the next place that we might put the value. So the depth of this tree is 0, 1, 2, 3, or 0, 1, 2. So the depth is going to be the greater of those, so it's 3. All right. So we know that we have that 3 is the nodes on level 3 where we know there's room for our next value. There's room for 8 things. So the next available slot is on level 3. So now to figure out where it goes on level 3. How do we know that there is that available slot? So if I go back in here, the actually what I want to do, I don't want to go there yet. Let's just operate in our current thing that it's going to be on level 3. We need to make sure we have room on this level, but this kind of solves itself with the way we're going to end up doing this. All right, so we're going to put this guy on level 3. All right, so the destination is level 3. In our example, there are currently 3 elements placed at that level. There are 3 elements currently in level 3. And we can represent the number 3, 0, 1, 1. All right, so it's the binary equivalent of the number of elements already placed at the level where we're going to be putting this. Okay, so we got that. So how do we use this information to find the next available spot? So all we've done so far is we figured out how many total nodes are in the tree, where's the level that we're going to be putting the thing, and how many things are already placed at that level. We know if we're at level 8, it's 2 to the 3rd power. We have 8 total elements that could go there. Out of that 8, we currently have 3 elements that have been placed, right? So instead of representing that in decimal, because I've alluded to, we're going to be using bitwise operators here, we're going to represent that in binary. 0, 1, 1 is the binary number 3 for the number of elements that have already been placed. I just want to make sure I'm very clear on that. This 0, 1, 1 is not because we're on level 3. It's because of the number of elements we've placed on level 3 so far. Maybe could have used a different example in that case where I wasn't operating on level 3, but that's just not what happened. All right, so 0, 1, 1, this represents the number of elements that already exist on whatever level we're going to be placing our destination. All right, so we're going to be using this thing called a bit mask. Talked about that a little bit last time with the bitwise ands and the bitwise ors. Okay, where ands let us keep just the bits that we are interested in. Okay, so let's say we have an 8-bit register. We talked about this, and we talked about these bit masks. So if I wanted to keep just the left 4 bits of this guy to get me the 1101, I can mask it by 111000, and that would just give me those far left things, and then we right shift to get me to the next stuff. Okay, so bitwise ands allows me to extract individual portions of a number. That's what a bit mask is. So this is what I was talking about before, this idea of GPS for heaps. I like to think of it as GPS for heaps. This guy tells us what direction we're going to turn. So now that we know the depth of our destination, we're going to need guidance to traverse our tree to the right place at that depth. Ultimately, what are we trying to do? We are trying to discover that this is the next place that we're going to put our value. That is the right child of this dude. All right. So ultimately, we want to have something that says, okay, I'm at the top. Do I go left or do I go right? Well, I go left. I'm here. Do I go left or do I go right? Well, I'm going to go right. I'm here. Where do I place it? Do I place it left or do I place it right? You're going to place it to the right. That's where his new location is. Okay, so we're looking for a mechanism that will deliver that information to us. All right. All right, so based on our example, we'll take the number of levels, 3, and we're going to 3 minus 1 to this to get to the steps to the parent of our final destination, and that's what I said right here. we're looking to get ourselves to this place right here. The parent of the child that we're going to place. Okay, so this guy right here is the parent of our next available spot. That's what we're trying to do. This tree has a depth of 3. We know that the answer is going to be at level 3. So what will I do? I need to traverse twice to get me to my, until I'm hovering at the parent ready to place the destination. I wonder why that keeps going off like multiple times today. All right, so we need to take 2 steps to hover above our destination. All right, so we're going to use this thing, a Bitwise Mask, for this GPS idea. So for our bit, we're going to have we're going to left shift a 1 by the number of levels -1. All right, and we're going to keep going. So we're going to start this variable bit. So this is like this is code. All right, so we have a for loop. It's going to start off a counter bit. What bit are we currently looking at? And it's going to start off at whatever 1 left shifted by our levels -1. All right, so we'll start bit off at 1 left shifted, which means multiplying it by 2, right? n-1 times, so 2 times. So that means our bit's going to be 1 times 2 is 2, 2 times 2 is 4. All right, so we're going to keep going as long as the bit is not equal to 1. And what are we going to do each time? We're going to divide it by 2. So we're going to go from 4 to 2 to 1. But we're going to keep going as long as it's not equal to 1. So we're going to do something on 4 and 2. 2 steps. That makes sense? Now we might say, well, why didn't we just count? If we're doing something 2 times, why didn't we just say I equals 0, I is less than 2, I plus plus? Well, it's because of how the bit mask is going to work. We're going to be using this value to actually do the mask. All right, so that's why we're specifically starting bit off at a value. So if I kind of show you on a, I'm going to rewrite this on a separate, I already have it written that way. No. Let's give ourselves this guy. All right, so we're going to start this counter bit off at the number 1 left shifted by n levels -1. So our depth is 3, -1 is 2. If I took the number 1 and I shifted it left by 2, I get a 4. Make sense? Okay, so that's what that became. So we just turned the weird shifty looking stuff into, that's actually the number 4 in our example. We're going to keep going as long as bit is not equal to 1. So that part's not scary. But what are we going to do to bit each time through here? We're going to divide it by 2. So this is bit is equal to bit divided by 2. That's effectively what we're doing. Does that make sense? So the first time it's 4, the next time it's 2, the next time it's 1. All right. So make sense what that loop's doing now? Go through twice. There must be a reason why I have this represented this way. And what I'm going to do, just for the sake of keeping track of this, I'm going to store the current value of bit in its binary format just for us visually. So a 4 is 1, 0, 0. Correct? This is the ones place. This is the twos place. This is the fours place. So we have a 1 in the fours place, a 0 in the twos place, a 0 in the ones place. That's the number 4. All right. So hopefully you're going to start seeing that kind of alluding towards our mask. If I'm looking at this, if I do a bitwise AND with this guy, I'm only going to keep that far bit. When I divide it by 2, that's the number 2. I'm only going to be keeping that middle bit. Gonna see where we're going with this. So this idea of counting down, dealing with dividing by 2s, allows us, if we choose to use a bitwise AND, to extract values. You could also do stuff with bitwise ORs, but we're going to see how this works out. So we're going to start bit off at the number 4 in our example, which is represented like that. All right, everybody good so far? Okay, we're going to keep going as long as bit's not equal to 1. Each time through, we'll divide it by 2. All right, so this loop's going to go through a couple of times. So now we need to make the choice. So inside of our loop, we're going to ask a question. I'll actually drop this down one that we have to think. We're going to ask the question, if n, okay, so which is our depth, right? N is 3. If that bitwise ANDed with the current value of bit, if that's equal to true, then that means we need to turn to the right. All right, so we'll see how this goes. I'm going to write the code in here. So we're going to say if n, which is 3, or I'll actually go up here and I'll set n equal to 3, the depth of our tree. All right, good with that? That's where that n came from. 3 is the depth of this tree in our current example. Okay, so n is 3. So if 3, well, I'll call it n down here since I'm going to be using bit anyways. Bitwise ANDed with bit. I'll just spell it out here if that equals true, just for our own visual comfort. Go to the right. So if this was true, our GPS location is going to say go to the right, and we'll follow this here in a second. Else, go to the left. All right, so first time through. Is this a me thing or I drug the thing up thing? It's that. All right, so we started off with bit is 4. We come in here, we take 3 bitwise and 4. So let's draw our n is equal to a 3 is 0, 1, 1. Make sense? So what does that boil down to if I do a bitwise and? That's 0, 0, 0. 1 bitwise and 0 is 0. 0 bitwise and 1 is 0. 0 bitwise 1. Bitwise and 1 is 0. So my answer is 0. 0 is a false. So if you really want to write this way, you could say if it's equal to a 1, do that. That's what true means. Else, do this. So the first time through, I bitwise and bit and n, and I got a 0. Was it a 1? Nope. So we'll go to the else. We're going to go to the left. So if I start at the top of the tree, my first GPS location is that. Went to the left. However, we're going to pull that off. So far, so good. All right. Now, I spin back up. I divide bit by 2. That's 0, 1, 0. Go ahead. No, this is, I mean, it's an int. That's just the name of the variable. Yeah. Well, the number 4 and the binary 1000 100 is the same value. I'm telling it to you in decimal and I'm telling it to you in binary, but it's the identical value. So even though we see this integer called bit being equal to 4, under the hood, it's actually represented in binary. We couldn't write it in binary, but we effectively did. It's still stored that way. So if I took a 4, well, if I took a 3 and a 4, I'd get a 0. So let me go out here to this guy. I don't really have like a, well, I'll just use my 300 starter for this. Oh, I was using that last time. Well, no, I wasn't. Doesn't matter. We'll just dump this. So if I say C out a 4 bitwise ANDed with a 3, it's probably going to want me to put this in parentheses. I'll get a 0. So it did the bitwise version. So the binary version of 4 bitwise with the binary version of 3, because under the hood, that's how computers store it. This 4 and 3 thing is for our eyes only. So it's not that we are storing it one way versus the other. They're the identical numbers, just represented in English versus Spanish, something like that. The number 7 in English is the same thing as, was it siete? Siete. Did I get that right? I know enough to order a Taco Bell. I think that's right. I think it's siete. Those are the identical values, though, said 2 different ways. All right. So first time through, 4 bitwise and 3, I got a 0. So that said go left. So I'm going to go to the left. We're just visually doing this. We'll figure out how to actually make it go to the left. Next time through, what did I do to bit? I divided bit by 2. So a 4 became a 2. Right? 4 divided by 2 gives me a 2. Before, this guy was a right shifted by 1, which we saw left shift multiplies by 2, right shift divides by 2. So when I say bit is equal to bit right shifted 1, this is identical to saying bit is equal to bit divided by 2. Means the same thing. But since we're dealing with the world of bit shifts right now, that's why they wrote everything in a bit shift format. All right, because initially to get that 4, they had to do a left shift on 1 n minus 1 times. Remember, to get this original 4, we had 1 left shifted n minus 1 times. 1 times 2 is 2, times 2 is 4. 3 minus 1 is 2 times. Okay, so that's why I just replaced that guy right there with the number 4. But he actually was, we calculated that based on a bit shift, this number minus 1 times. All right, so we moved left the first time. Now we divided bit by 2. So bit is currently a 2. Is it true that 2 is not equal to 1? Yeah, it's a true statement. 2 and 1, different numbers, right? All right, so we'll come in here. We're going to ask the question. So 2 bitwise ANDed, whatever n currently is, which is 3. 0 and 0 is 0. 1 and 1 is 1. 0 and 1 is 0. Okay, so actually I'm going to write this a little bit different way. I've kind of misrepresented this a little bit. It's actually, is it not equal to 0? I think I've mentioned that before, that true something being true does not mean it boils down to 1. It means it boils down to something other than false. False is 0, so true would be not 0. So this guy boiled down to the value of 2 in this case, which is something other than 0. So I'll go to the right. So the first move, I went to the left. Second move, I went to the right. Make some sense? That gave me my 2 moves. Now, loop back up. Bit is equal to bit divided by 2. That's that guy. Then we say, which is the number 1, correct? Is bit currently not equal to 1? That's false. He is equal to 1. So I'm done. I've made my GPS moves and I'm currently hovering. I'm sitting at the parent of the location where I'm ultimately going to go here. All right. So now we need to decide, what do we do with that? So now we're positioned right above our goal, but which child should it be? We could just ask the question of what is open, or we can keep using bits. So I know that I'm dealing with a binary tree here, right? So I could just write this as an if statement. If I'm sitting right here and I'm that parent, I'm looking down and I see, well, I got a left child. I don't have a right child. That's the next space to put them, right? I could do that, right? No problem. Or we could look at it from a bit perspective. So kind of a, a landing, time for landing. I'm at the parent thing. So n is 1, or I'm sorry, n is 3. If I bitwise 3 by 1, if that's a true statement. So if I say in this case, n is 3, 0, 1, 1, and 1 is 0, 0, 1. And I bitwise and those guys together, I get 0, 0, 1. Is that guy not equal to 0? 1 is not equal to 0. So we would get into this if statement and we'd set the new node as our right child. Else, I'd set it as my left child. That make sense? Okay. So ultimately, we placed it in this case. It's our right child. And once we got here, you could figure that out either way. Keep using bits or just ask the question. Frankly, they're both asking a question, so I'm not necessarily sure one's better or worse than the other. I mean, it didn't matter whether we asked this question here. Let me just take that stuff away. So we're just looking at the algorithm. If I have to ask a question anyways, I could just say, if I don't have a left child, if left child is equal to null, place it there, else place it on the other one. I'm still asking the same number of questions. And generally speaking, when you think about the efficiency of an algorithm, we are usually, it can be a little bit deeper than this because we can maybe ask the question, well, which is more efficient, doing this math problem or checking to see if a certain memory address contains a value or not. If we drop down to that level of detail, we say, well, if I have one guy checking on the value at a memory location, and I have another guy just doing this math problem, who wins? Who actually does that work faster? From a human being perspective, they're both going to happen instantly, right? So we can say that they're both really, really, really fast. I'm sure that if we actually measured this at the microsecond, one of them probably would be the winner. One of those two questions probably gets asked a little bit faster than the other one. So if we were being ultimately optimized, we could come down and say, this is the choice I should make. I'm not even sure which it would be. Doing the math problem, probably math. My guess is, especially since it's bit shifts, it would probably be math would be faster, but not fast enough to make the decision. So when you get to this level, if you just want to ask where to put it with an if, it's not going to hurt anything. All right, but if you're already in bit shift mode, you can ask the question in a different way if you want. All right, that makes some sense how we can use bit shifts with masking to traverse our tree down to our place, as opposed to using the array implementation that we looked at initially. What was really the difference? The array implementation said, well, I'm going to go ahead and effectively draw out my, I'm going to draw out my current bottom depth of my tree, my binary tree, into an array. And then I'm going to look where there's an empty bucket. Now we might say, hey, that makes pretty good sense if we looked at a different heap implementation. So if I go back to this guy, to heap data structure. Okay, because I mentioned when we first started talking about heaps, we talked about a heap as being a priority queue. And when we think about something as being a queue, we're thinking like a line at McDonald's. Okay, so if I'm visualizing as a human being what a line looks like, I'm not visualizing a tree, right? I'm visualizing a bunch of people in a single line. So with that in mind, I might say, you know what? You walk into a McDonald's, you might kind of glance at the amount of space in there, and you might decide, okay, the maximum number of people that can be in this line is 100. Just making up a number. Now, as modern day computer users, we might say, well, if I'm going to store 100 things, is that really that much given the amount of memory we have in our computers today? Probably depends on the types of things we're storing, but if it's people objects, let's say, where they have a first name and a last name and an amount of money in their wallet or something like that, we might say those aren't huge values and we're only going to store the pointers to those places anyways. We might say, okay, well, let's just go ahead and create an array with 100 buckets in it, and we'll just start filling it up, even though I know a lot of the space for the line is currently not being taken up. And if we had that, when somebody comes in to to McDonald's, before we let them cut in line, where do they go? They go to the back of the line. That's the next open spot. So this exact same tree that we have right here, in an array format, so front of the line, we're dealing with, in this case, it's a min heap. So this is the front of the line, this is the back of the line. Somebody walks in, what do they do initially? Get into the back of the line. That seemed like it was a whole lot easier to find the next available spot, wasn't it? At what cost? Well, some memory inefficiency. That's the whole reason why we look at linked data structures. Now, we could say, okay, well, if we want to be super memory efficient, we could have implemented this instead of as an array, we could have done it as a linked list. All right, no problem. So now we have a linked list, but presumably we can just add this guy to the end. Pretty easy. Up to this point, An array or a linked list is better than a binary tree representation when we consider implementing a heap. All right. Because all that crap we just did up here could be replaced with just go to the end of the array. Next bucket. Next available bucket is the end. All right. And remember, we talked about min heaps versus max heaps, and I want to look at implementations here. It's not going to give me an array comparison. Maybe it does it with the priority queue. I wanted it to give me speed comparisons for the heap versus priority queue. No, doesn't matter for the moment. For us right now, we could just assume these are two different implementations of the same thing. But now we want to think, what would it take to get the person? We just keep thinking about it like this is a line at McDonald's. What would it take to get to the person to the right place in the line, whether we're dealing with a linked list or whether we're dealing with a array. So we're going to look at the binary implementation. I think we had already been on that. Where's my binary link? All right, so here's our binary. So we added the element to the bottom level of the heap. We've accomplished that now with our binary tree with all these bit shifts and stuff. Now, if you go back and look at this, even though it was a little bit confusing to walk through, the actual loops for this was not that bad, right? This is a pretty easy for loop. It just looks intimidating with bit shifts and stuff. It's not like we have 200 lines of code that's making this happen. All right, just kind of plinking down the thing, and then we finally ask one last question where, you know, once we're at our position, we just ask, you know, if left child is available, put it there. Else, put it at the right child. That's effectively the algorithm for placing it. This code right here. Not too horrible. But that only starts it. This is the insert thing. So I place it to where it needs to go. Then I compare the added element with its parent. If they're already in the correct order, we stop. All right, so go back to our tree here. I placed it down here. So this guy is going to compare himself to his parent. Remember, in this particular case, we're doing a min tree, right? So we're going to say he's already in the correct location now. So we would stop. The parent is already smaller than the child. So we're done. Let's just switch this up a little bit and we'll make that a 1, just so we can get past that first test, right? So we just place this guy, the 1, and we're going to say he's going to compare himself to his parent. He's going to say, is my parent greater than or equal to me? So this is a min heap. It's not. Okay, so if not, we'll swap the element with its parent and return to the previous step. So these two guys get swapped. And now we're sitting here. This guy then asks his parent, are you greater than, or let's see, are you less than or equal to me? If yes, stop. If no, which in this case, he's not, they're in the wrong order, I will swap these guys. Now I'm here. Now I'll ask the question to my new parent. Are you less than or equal to me? Yes, I'm equal to you. You're where you belong. So now this guy has been inserted into our heap. That make sense? So, question is, how would you implement this if we are walking up this? If I'm comparing this node, so consider that we just finished placing it. So at this point in my algorithm, I know about this parent. I also know about this guy. Now, presumably, I think I mentioned when we first would write our binary tree for this, we would probably write it as a doubly linked binary tree, where any node can traverse to its parent as well as traverse to its child. Because with a heap, we need to be able to walk up the tree to accomplish some of these steps. Okay, but the interesting question here is going to be this: depending on what we're storing in the heap, our payload. We want to think about our linked, whether it's linear or nonlinear linked data structures, as nodes that have payloads as part of them. In this case, we know this 1 and this 5 should swap places. But the question is, does this node have to move down here and this node have to move up here? Or can we just swap their payloads? Is this node, forget about the number that's inside of it, any better or worse than this node? Other than the fact that he looks like a star, so he's probably better. But but a node is a node, right? If we don't think about the value stored inside of it, a node is just like any other node. So we don't gain anything by actually having these physical nodes switch places. Right? We don't gain anything by having these physical nodes switch places. All we have to do is say, oh, I'm just going to swap the payloads. And then keep going. Now, and then he follows. And I say, oh, is this guy in the right order? Nope. Swap the payloads. Then follow him. This is my cur node. Is this guy in the right order? Yes, we're done. Notice actually, if we do it that way, it's not really bad. Because we didn't actually have to do like reconnecting pointers and things like that. We just said, hey, I have a pointer to this guy. I have a pointer to this guy. They're in the wrong order. Swap their payloads. Don't disconnect anything and plug it back in. Just change the values that they each hold. Temporarily hold the payload for one of them, overwrite it, and then put it back into the other one. All right, that makes some sense? All right, so hopefully today we kind of have an appreciation for in a live situation where we could use ands and shifts to accomplish something that might be meaningful. Not that you're going to bump into that really, that often, but here's a real life example of where those things can come into play. Cool. All right. So we'll come back on Friday and we're going to start looking at on our next data structure. We're going to say we kind of killed these heaps and stuff. So we're going to start looking at graphs and start moving towards the traveling salesman problem. So I'll see everybody on Friday.